IL is for overhanging beam. Okay, overhanging beam. We will develop ILDs. So everything is easy based on that. What we develop, how can we develop it? See how we will develop. So we will place the load at particular instances. We write the quantities. Later we will add it by a line. See every IL is in this determinate structures. Determinate structures. We will develop only for determinate structures in this course. Determinate structures. Everything is in straight line. Straight line, not a curve. Not a curve. Curve will develop for indeterminate structures. Indeterminate structures, it will looks like a curve because the quantities are dependent on square terms, cubic terms. In this, the quantities are everything is in a arithmetic, linear variation. That's why everything is in straight line. And also for the determinate structures only, we can find out the quantity easily if load place. So how we develop? How we develop? See how we develop. So we place the location of this place and we find out the RA. RA. So RA is 1. At this place, RA is 0. At the center, RA is half. That's it, na? If we put to 1 unit load, it's half. So based on that quantities, find out the quantities of every location. Later we draw ILD. So at this place it's 1. This place 0. At this place half. At this place 1 by 4th. 1 by 4th. No need to calculate every point because we can join by a straight line because this variation is this straight line variation. So we develop like this. So we can easily calculate these parameters because these are determinate structures. For indeterminate structures, you can't find out. For the how we will solve indeterminate structures, we have been studying from first class to this class. It's a hectic process to find out one quantity at particular loading. But if you're changing the loading to find out the quantity is too much. See, too much simulations are there. Okay, so that's it. You have to find idea. We are only develop determinate structures, and everything is in straight line, not a curves. Okay, so how we develop like this each quantity and we'll draw it. That is ILD diagram. So now we will see overhanging beam. Overhanging beam, it's A, it's B, its length is L, something if its length is F, its length is E. Okay, so this is D, this is E, and we can take C as its center for location of any one quantity. Okay, for C is certain one section, particular section, we have to draw influence line for shear force, we have to draw influence lines for bending moment. That's it. See, first we have to develop ILD for RA. So reaction or A or B. Okay, just look it. You already know when the load is at here, when the load at A location, RA is 1. Exactly RA is 1 because support reaction exactly it matches equilibrium. So same thing at load at B, RA is 0. At load here, RB equal to 1. That's it now, RB equal to 1. So RA is must be 0. Okay, these are the quantities you already know. No need to discuss. So next we have to find out. See, we have to find out when the load is at here, when the load is here, when the load is here. So load at D. At D, what is RA? Everything we calculated RA, influence on RA. When the load is moving from one end to the other end, what is RA is changing? That is influence. See, calculate RA. So do it, So how can you do it? So at D, so do it. So we will do multiplication. So moment at D is 0. RB into L plus E plus RA multiply with E must be 0. That's it, no? Must be 0. So what is RA? RB into L plus E is equal to RA multiply with E. That's one thing. And also you can find out RA plus RB should be 1. RA plus RB should be 1. That's it, na? So you can write down RA RB. See, RB in terms of RA 1 minus RA. RB is equal to 1 minus RA. So you can place it. You can place it 1 minus RA L plus E is equal to minus RA into E. Okay. So write down L plus E minus of RAL minus of RAE is equal to minus of RAE. So you can cancel it. You can cancel it. L plus E is equal to RAL. So RA is L plus E by L. L plus E by L. Understood? That's it. So L plus E by L positive. L plus E by L. So same thing. You can just imagine. Imagine when the load is at when the load is at center, that's called C. You can call it C. When the load is in exactly L by 2, what will happen? When the load is at C, you already know RA is exactly half. That's it. Equally distributed RA, RB, half. So now we will see when the load is at here, 1 unit. When the load is at E, when the load is at E, when the load is at E. So what is? So you can write down same thing. You can derivate it. So once again same. See. So once again moment at E is 0. You can write down RA multiply with L plus F. L plus F, na? L plus F plus RB multiply with F is equal to 0. And also RA plus RB should be equal to 1. Okay. So now develop it. Same once again you write it. RB is 1 minus RA. Place it. RA L plus F 1 minus RA F is equal to 0. RAL RAF minus F minus F minus RA into F equal to 0. Okay, minus F into is equal to 0. That's it, na? That's it. So cancel it. Cancel it. Cancel it. RAF cancel. RAL is equal to F. So RA is equal to what? Minus RAF F by L. Okay, RAF by L. That's it, but it's can't. RA plus 1 paragraph. Sorry, this is plus F. Okay, sorry, that's plus F. It comes to minus. Okay, that is plus F. Okay, see it. So RA is minus F by L. Understood? That's it. Once it's a opposite direction. That means what? RA is not in this direction. It will come to bottom. Okay, overhanging beam already you solved in previously in strength of materials. So okay, what is if you see, just observe it. previously. Not only you can observe it, you can also find out the same in RB also. No need to again draw for RB. So at the same situations, you can see first situation RA is L plus E divided by L. So what is RA? RB? RB is 1 minus L plus E by L. So what will come? L minus E by L. RB is minus E by L. So in this place, RA is 1 minus F by L. So see RB is 1 minus FA, 1 minus L. So it becomes to L minus F by L. Okay, L minus L minus, it will come plus. RB is 1 minus RA. RA is minus F by L. 1 minus F by L. RA is RB is, it's okay, no need at all. So I will show you. So see, we'll draw. So draw RA. Draw RA. So okay, RA, draw it. So see, when the load is at A, that is 1. You have to, you know it. It is a 1. You can draw it 1. When the load is at B, it's a 0. At the center, it's a half. It's a half. It's a 1. Okay. So next, when the load is at when the load is at D, when the load is at D, what is value? When the load is at D, L plus E by L. L plus E by L. So this is will come L plus E by L. You can just add it. It will straight line. It is exactly straight line. Okay. This value is L plus E by L. So when this load is at B and the load is at E, when the load is at E, what is the value? Minus F by L. Where it is? When the load is at E, minus F by L. Understood? So minus F by L comes to this. This is F by L. This is ILD for RA. This is ILD for RA. Okay? So that's it now. That's it. So you already know. Otherwise, if you just clarify it, just do it. Just do it. Just do it. No need to yell and something. This is taken as a 1. See, this is taken as a 2. This is 2. This is 2. Just observe it. When the load is at 1. What is RA? What is RA? It's compulsory greater than 1 by 1. Greater than 1. It will comes to negative value. Otherwise, check it is. RB multiplied with 4 plus RA multiplied with 2 is 0. So if you just observe it, RB4 is equal to minus RA multiplied with 2. RA multiplied with 2. One is positive, one is negative. Understood? RA is positive, RB is negative. One is positive, one is negative. If you take in any overhanging beam, the load is on the portion of overhanging. The load is on the portion of the overhanging. One support gives vertical upwards, one support gives downwards. So again, for RA plus RB should be 1. So RB you can RA you can write as 1 minus RB. You can just check it. What is RB? So check it. RB multiplied with 4. RA 1 minus RB multiplied with 2. So minus. Check it. RB4 minus 2 minus plus 2 RB. So 2 to cancel. 2 RB equal to minus 2. RB equal to minus 1. See it is. See it is. It is a minus 1. It's a 2 will come. 2 minus 1 equal to 1. 1 equal to 1. 1 should be equal to 2 minus 1. Na? 2. This is minus 1. See, just check it. So any overhang beam that will come. It will come as RA is 1. RA is 2. This will comes to minus. So one reaction will comes to this and another reaction will comes to this. Because the moment is overlapping. Overhanging moment to support that. It will comes like this. You already solved so many overhang beams in strength of materials first unit, I think. That's the case. RA, when it is, this is the ILD for RA. RA is greater than 1. Greater than 1 will come. when the load is this portion. When RA is negative, when this portion will come. If you just observe it, it is just a straight line. There is no change at all. This is exactly a straight line. Same slope, maintaining a same slope. I understood. Same thing. Same thing. If you write RB, RB also. See it. When the load is at A, RB is 0. When the load is at a B location, it will exactly equal to 1. Exactly equal to 1. So at center, it will come as off. It will come as off. When the load is at this position, D position, RB is negative. What is that value? Negative will come same. If you see, observe it, you can derive the same. It will come like this. It will come like this. It will come like this. It will come RB is E by L. This is negative. Same here it will come L plus F by L. It will come. Check it is. Check it is. Otherwise it will say. Understood? That's the position. That's the exactly overhanging beams. You have to develop the ILDs like this. You have to place load at every position. How the parameter is varying. How the parameter is varying. Are understood? But once again you can observe it. This portion is same exactly. This portion is same exactly for simply supported beam. First cut it, otherwise check it is. This is an exactly for simply supported beam. Only overhanging is, if you attach overhang, it will come like this. If any beam or any situation, if you attach a overhang of one end or two ends, if you attach, it will come like this. Now you can easily draw overhangings of just one end. If like this is the overhanging. Can you write a RA? RA is, can you write it? Just it. This is 0. It will go same slope. That's it. This is RA. So what is the portion here? Based on that portion only you can say. See, it is L. It is some R. You can write it. So this is minus R by L. Same if you write this. If you write like this, RB. This is 0. This is 1. This is RB. You can write it. It will go like this. RB. For RB. So gauge line. So this is what? L plus R by L. It will come like this. Same you can observe. Understood? So in this has you can directly, you got some idea. So no need to find out these values. You can directly draw a straight line. Is it okay? Is it okay? You can directly draw a straight line because same slope, there is no change at all. Can you directly write down the influence diagram without knowing these parameters, without finding these parameters? Yes, you can write it. How can you draw ILD for without finding the parameters, without finding the influence of on parameter for different positions of load? I will show you based on the Muller-Bristol principle later. One dedicated class for that principle. You no need to find out this exactly these calculations. No need to find out these calculations. You can directly draw ILDs. How can we draw? So later I will show. The same thing now you can draw shear force. Shear force diagram. Shear force diagram. Same principle, same you can. So same overhanging beam. I want shear force at this location. So I want shear force at that location. Okay. So this is A. This is B. So total length is L. So this is E. Previously said this is F. So O shear at C. Shear at C. So yesterday we developed shear. So see, no need to find out everything values. Just in center it is a simply supported beam. Already we developed. How it is developed? So this is A, B. How it is developed? Just shear at that location. Just to displace. So what we developed yesterday? This is A by L. This is B by L. That is A by L. This is B by L. Exactly. That's the only exactly write it. But remaining, sir, overhanging portions, how can develop? Just extend it. just extend it. Here also just extend it. That's it. Same continuity. This is a compatibility or continuity. Sir, what is this value? This value is C. This is E by L. This is F by L. That is a shear at C. You can directly, otherwise you can directly find out. So you can find out, sir, we have to place this. I place a unit load here. I place a unit load here. What is the shear force? What is the shear force at C? So if you load a place here, so what is RA? So now we can, otherwise I will try it. See it. Load place at D. So what is RA? We already developed. What is RA? L plus E by L. L plus E by L. That's it. Na? So what is RB? What is RB? RB is minus E by L. We developed same thing. See where it is. So we already developed minus E by L. So now you can find out the shear at C. Can you find out? Can you find out shear at C? So easily you can draw. Otherwise draw shear, just shear. So this is, what is the load? Load here, just this is a load of 1 kilonewton. 1 kilonewton. 1 kilonewton load. 1 kilonewton load. 1 kilonewton load. So opposite, I think. Opposite. Just place the loading diagram. Loading diagram. So this value is what? This value is L plus A by L. So you can write on this loading diagram. Just load. So otherwise you can find out the shear directly. No need at all. Just this is a 1 unit. So sorry. This is a 1 unit. So what is RA? RA is L plus E by L. L plus E by L. So what is the shear at this location? What is the shear at this location? 1 minus, this is 1 minus L plus E by L. That is the shear. No? So you can catch it. It's a minus E by L. Minus E by L. Minus E by L. At this, exactly at this location. At this location is what? Minus 1 minus E by L. So shear. So at this, okay. So same thing, it will come at this position, at this position, at this position, at this position, same. Minus E by L. That's exactly minus E by L. See? E by L. Are you get it? So I think, so shear from this location, so you will get positive sign. Because this will take as a negative. I will directly write absolutely. So exactly if the load is placed here, what is the shear? E by L. If exactly load is here, so RA is exactly 1. So what is the shear at this location? 0. 0, you will notice it. So if you place load here, place here, this will come as a 1. This will come as a L plus F by L. So you can find out the shear 1 minus that value. You will get is F by L. Are you getting? So exactly if you place in center, if your load is in between the simply supported beam at the, that is exactly replicate of previously we solved it. So previously yesterday we solved it. If the load is exactly in between A to B, that is simply supported beam. How we will develop? We develop it. So no need to discuss again in between A and B. We are only interested in overhanging force because this is exactly looks like simply supported beam. So if the load is in between A and B, there is no other load and overhanging. Those overhangings are just looking purpose, nothing use. Okay, if the load is there, if it is overhanging beam is there, if the load is in between, it's exactly simply supported. What is the use of this? Nothing. Waste luggage. No loads transferred from this position, from beyond that points. Okay, that's it. No? So exactly if you see the load is at this location, the shear is E by L. If the load is at this position, shear is F by L. At here at particular value, particular location only, not a shear force diagram or something. Got it? So that's it. Same thing. This is a negative. This is positive. Same. This is positive. This is negative. So okay, shear. So same thing. Bending moment also. You can write down. So bending moment diagram at C. The load is moving, bending moment diagram. Same thing, no need discuss. See it is between A and B. Previously, yesterday we developed. What is developed? That's it, huh? That's it. What is that value? That is AB by L. AB by L. So remaining for overhanging portion, you can extend it. You can extend it. Sir, what is this value? This value is EB by L. This because this is E. This is F. This is what? This is FA by L. Sir, how can it is? How can I trust it? No need. Do it. Do it. So I will show you. No need. So what I develop? So this is a overhanging beam. I applied a load here. I want a moment here. I want a moment here. I want a moment here. That's it. That's it. Just it. So no need at all. Just see this. If you want, this is a unit load. What is this value? This is E. What is this value? L plus E by L. What is this value? This value is below. This value is exactly this value is E by L. That's it. This value is E by L. We already developed it. If the load is at this location. So find out the moment at this. Find out the moment at this. So moment at this from this right side or left side. So for right side, it's two quantities are there. You can find out the left side. So bending moment you can find out from left and right. So see E B by L. So nothing. That's it. E B by L. So same thing. Same thing. A B. If the load is there, if the load is here. So what is the quantities? This quantity is L F by L. This quantity is F by L. So we want moment here. So this is B, this is A. That's it. So if the load is at the end, so these are the reactions. These are the reactions. So what is the moment at here? So you can't from this because we have two quantities. So you will get from this. So what is the quantity? F A by L. Say F A by L. Are you getting it? So F A by L. So this is the opposite direction, bottom direction. That's why it's negative. Got it? Got it? That's the way you have to develop the bending moment diagram. See, shear for C. ILD is for any quantity, either shear reaction, either shear, either bending moment. For any location, you can try it. So for simply, so you have to find out so many number of quantities because so many positions are there in a beam. The load is moving from one end to the other end. The parameter is changing. How it is the parameter changing? The parameter is some shear force or reaction. Okay, but the load is moving from one end to the other end. So many positions are crossing. So we have to find out some key positions. Key positions means that's it. When the load is here, one key position. When the load is here, one key position. When the load is center, some key position. When the load is at so many number of positions are there. So we have to find out at every instant what is the parameter is changing. Sir, this is somewhat hectic. This is very simple problem. These are the simple problems. If you go to the hectic problems, you will feel hectic. So how can you draw simple? That is the Muller-Bessel principle. We will show later. Okay, that's the way you have to draw ILDs. This is ILD for bending moment at this location, C location. Where it is? This location. This is the shear force for this location. So okay, so by the same idea, I will develop for this another beam also. So okay, I will just give a training how the IL is. Okay, so the section is now cantilever. This is a determinate beam. Determinate beam. This is a cantilever. So can you develop the ILDs? So this is A. So for RA, develop RA, develop ILD. How is one unit load is moving from one end to other end? RA is changing. See, you can directly draw. So how can you draw, sir? Exactly the unit load is placed at A location. What is our RA? That value 1. Exactly RA is equal to 1. If it is load is there, RA is what? 1. If the load is at here, what is RA? That is also same 1s R. That's a, this is L. If the load is here, what is RA? Because only one reaction is there, compulsory it should reflect total value. RA is 1. If the load is here, what is RA? RA is 1. So what is ILD? ILD is this. This is RA. This is 1. Understood? That's it. That's the way you have to develop ILDs. Okay? You have to develop ILDs like this. Okay? So next, develop it. Next we have to develop bending moment at A. This is for RA. So now bending moment at A. So develop it. Bending moment. So load is same. Load is at here. Load is at position A. What is the bending moment? No bending moment, sir. So if RA is, this is 1, this is also R is 1. Bending moment is 0. No bending moment. Are understood? 0. If the load is certain position, here position, so no need to take it. So I will take it N. That is the best choice. If the load is at, this is 1 unit. What is the bending moment? What is the bending moment at A? Only bending moment at A. So 1 multiply with length, sir. That's it. 1 multiply with length. So 1 into L. 1 into L. It's a negative sign. It's not. It's going to be this direction. So we will write bottom. This is L. So if the load is here, what is the bending moment at A? So low. This is, sir, this distance. What is the distance? We don't know. Okay. So 1 into this distance, sir. That's it. Na? So 1 into that distance means distance is decreasing. Na? Decreasing. So maybe its value. So if the load is here, moment is what? Bending moment? Bending moment is load into that distance. So distance is varying linearly. L to 0. So that's it. That is the moment is varying. That's it now. If you see, the load is some 20 kilonewtons. Length is 4 meters. If the load is at here, if the load is 20, it's a 20. What is the bending moment? 0. The load is here, 20 into 4, 80. If the load is at 3 meters, 20 into 3, 60. If the load is at 2 meters, 20 into 4, 40. That is the moment, na? That is the bending moment. So bending moment, how it is bending moment varying when the load is moving from one end to the other end? So exactly it's multiplied with distance. 20 is constant. It's a 20 into 4, it's a 20 into 3, it's a 20 into 2. How it is changing? Multiply with, so with respect to the length. So exactly its length is changing from 0 to L to 0. That is ILD for MA. That's it, na? That's it. So now I want shear force at one section. Shear force at one section. What is that section? I will ask something. Okay. So certain section I will take it. This section I want shear force. I want shear force. How it is changing shear force. Just see it. Just see it. So shear force at C. Just see it. If the load is here, what is the shear at C? 0, because the load is 1. It is also 1. There is no shear. If the load is here, how the shear is changing? So see, draw shear force diagram. So this is 1. This is 1. So later it reaches to this position, it's 1 again. 1 opposite direction. That's the shear force. So exactly what is shear force at C? 0. Because this 1 cancel to this 1, the shear is at C 0. If the load is here, again the shear force diagram is looks like this. Shear at C 0. So up to the load crosses to that section, shear force is 0. That's it, na? That's it. It's a 0. Up to the load position is 0. So once it's somewhere the load is here. Somewhere is load here. What is the shear force at that section? You can easily set that it is a section. It has only 1 unit load. It is a 1 unit load. There is no change in shear force. There is no loads at all. So exactly the shear force at this section is 1. Otherwise, if it is 1, it is a 1. It is a 1. So shear force is at C. See, check it. It's a 1. Draw shear force. It's a 1. So up to this, there is no change. That is exactly shear force at that section is 1 only. Otherwise, come from right this side. See, only 1 is there. So load is at here. Again, same thing. Load is at here. Same thing. So what is the shear force diagram? Up to this is 0. Later, it's a 1. 1. That's it. That's it. So, and I want another. I want another. I want another. The same section, how it is movement is changing. Bending moment. Bending moment at that section. I want bending moment is change. How it is bending moment change? So again I will write. Bending moment at that section. So can you draw? See it is. The load is at here. Same one reaction will develop. Moment is 0. If the reaction, if the load is at this place, if the load is at this place, what is the bending moment at this location? What is the bending moment? See, just 0. So how get it is 0, sir? So what is the bending moment at here? If it is come from this side same. See this side there is no load at all. Bending moment is 0. Otherwise you can just check it is. This is a beam. I applied 20 kilonewtons here. It's a 2 meters. It's a 4 meters. What is the bending moment here? If you draw, so bending moment is what? 0. Because if you draw bending moment diagram, what is 20 into 2? It's a 40. It's a 40. It's a 40 bending moment. So where it's 0? It comes to 0 this. At this point it's 0. So 20 into 2, 20 into 1, 20, 20. This is 0. Later this is 0. Bending moment diagram. This is just a overhanging. Just a overhanging force. There is no nothing. Nothing will take care. If you apply 20 here, so it's a 20 into 2, it's a 40. At this place is 0. So remaining total is 0. So what is the shear force at this location is 0. So that means same thing. Same thing. You can see it. If you applied a load here, load here, everything is 0. At every position, the bending moment at this location is 0. Are understood? So up to this is 0. So later, so now I have applied a load here. So load I applied. What is the bending moment? Bending moment is just this value 1 multiply with this distance. And that's it. Bending moment is what? Exactly that's it. Bending moment. So at this location, what is the bending moment? So that 1 unit multiply with this length. So if load applied here, so what is the bending moment here? So that load multiply with this distance. So that distance is varying. Okay. So suppose this distance is A. So when you load applied here, what is the bending moment here? What is the bending moment here? 1 multiply with A. Here, when you applied here, 1 multiply with this distance. So when you applied exactly this location, bending moment is 0. So how it is varying? How it is varying? Same thing. How it is varying? When you applied here, that is A, 1 into A. So up to this 0. Remaining portion of everything is 0. That's it. That is bending moment at C. This way you can develop for any type of determinate structures. Every determinate structure is a straight line variation. There is no parabolic distributions, parabolic changes. Are get it? So now I will give assignment. Develop ILDs for sir. This is a proper cantilever. It has indeterminacy of 1. So you can't directly find out the reactions and moments. So sir, you asked me to develop ILDs for only determinate structures. How you gave indeterminate structures an example? So I won't give indeterminate structures as your assignment, but I will provide one hinge. here, and I don't need to give any LABC. I will directly give this is a 4 meters, this is a 6 meters. Okay. Develop ILDs. This is a hinge. Develop ILDs for A, B, and at this location. What is this location? This location is 6 meters from that position. Develop ILDs for RA, RB, and also shear at location of this is C, bending moment at this location of C. You can develop. Can you develop? So this is a hinge. You can easily find out RA is RA, RB, RC. So I will write down for RA. I will write down for RA. See, RA is what? Just see. When you load applied at here, RA is exactly same. Okay. When you applied a load here, what is RA? Sir, how can you develop it? So can you develop it? So see it. How can you develop it? What is RA? Sir, write down the equilibrium equations. Write down. But otherwise no need. Because see, if you applied one here, this is a hinge. We already said this is a hinge. So compulsory at this location is moment should be 0. If that is the moment, it should be 0. RB should be 0. Na? RB should be 0. Otherwise, the not moment is equal to 0 at this location. If RB has something, compulsory RB multiplied with the distance, it will comes to moment at something. But this is the position of hinge. That means what? The moment is compulsory 0. Because of this moment at this location is 0, there is no shear, there is no reaction developed at B. There is no reaction developed at B. So compulsory the total reactions taken by A only. Otherwise, just think a small idea. This is a hinge. There is no transfer of loads. There is no transfer. Transfer of loads is there. Just it will bend it. It will bend it. Total reaction taken by area only. So up this location, at this location. Otherwise, you can write down the equilibrium equations. RB multiplied with L equal to 0. So compulsory RB equal to 0. So RA is 1. You can write down one equation. So up to hinge location, RA is 1. So suppose, now the situation will come. The load is at up to hinge location. Okay. Up to this hinge location, RB is 1. Suppose load is at here, it is 0. We already know because RB is 1, so load is 0. So now you can see the load is at here. So what will happen? So again see RB multiply with 6, RB multiply with 6, and this load, what is that load? 1 multiply with this distance should be, the distance is some x, should be distance equal to 0. Sir, RB have rated. So that means what? See, that means what? RB into 6. RB is equal to that load 1 into some distance divided by equal to 0. RB has some value. RB got some value. Otherwise, see, RB has some value. Because it must be a bending moment is 0. RB has some value. RA has also some value. RB. So what is RA? If you got this is RB, RA is also has some value. So what is that value? So you can write down. So this is value. So you just need to take care of values. No need to some x. So I will just took it as a load is applied at this position. Because is this 6 now? I will apply 2 meters. So this is 2. So this is 1 by 3. RB is 1 by 3. RA is 2 by 3. So at this location it's a 2 by 3. At this location is 2 by 3. Okay, are understood? At this location is 2 by 3. So if applied here, what is that here? Here is exactly 2 meters. 2 meters from B. 2 meters from B. So what is exactly? Write down the equation. RB multiply with 6 minus 1 multiply with 4 equal to 0. RB is 4 by 6 is to 2 by 3. RA is 1 by 3. So at this location is 1 by 3. 1 by 3. You can just add it. You can just at this location 0. If you just add it, you will get like this. You will get like this. So up to hinge location RA is 1. After that it's going to be decrease. See, it's 1 by 3. See, it's a 2 by 3. RA is 2 by 3. RA is 1 by 3. So load position is shifting. So load positioning goes to forward from the hinge position. RA is decreasing 2 by 3 to 1 by 3. So you have to find out RA at different instances. You can just directly add it. That's it. So if you write down the RB, so I said that if this is RA, so what is RB? Previously I explained. So based on this only you can easily find out. Because see, RA plus RB should be equal to 1. That's it. Na? So if RA is up to this is 1, RB should be 0 up to this. Because RA plus RB should be equal to 1. Na? There is no other instance. There is no other loading. RA plus RB equal to 0. So RA is equal to 1 up to this. RB should be equal to 0. Otherwise just see it previously. If you applied a load here, the moment at this location compulsory 0. RB is 0. If you load here 0. Same thing 0 0 0. And after that RB is increasing. We already developed it. RB is here is 1 by 3 next to 2 by 3. So when you apply exactly hit this at this location, RB is 1. So this is RB is 1. So it will goes like this. This is 1. At this location is 2 by 3. At this location is 1 by 3. So if you have, there is no X and Y, just take it because I will give lengths. So you can directly take it. So this is RB. This is for RB. So for what? Bending moment at A. So I will ask bending moment at A. Bending moment at A. So now you can also develop shear at C, and also you can find out bending moment at C. Try to develop this and we will discuss later. Okay. It's almost 11. You have continuously class 9 to 10, 10 to 11. So at least I will give half an hour class rest for next class. Okay, no need to extend the class. Try to develop ILDs for MC, shear at C, moment at C. So shear at C. Okay, not a C. Where is this? Is a C. Okay, shear at C, bending moment at C. Okay, so develop it. Try to develop those values, and also bending moment at A. Also bending moment at A. Also develop. Try to develop. Take 2-3 instances. 2-3 instances. Where the instances? This is one. So try one loading exactly here, exactly A and B, and in between try to 1, and later try to 1. So 4 instances. If you have load applied here, here is very easy because those reactions will come directly. So there is nothing will come to zeros. So before hinge, after hinge. This is the determinant structures. Okay, are understood? You can directly develop loading. So, okay. Try to get these ILDs. Tomorrow we will see the syllabus. So we will see the remaining. Okay. So you can develop anything. So I will show the syllabus. Just one instant. This is advanced. We don't need. This is again advanced. See, structure on syllabus. Definition of influence line for shear force. Who wrote this syllabus?